Welcome friends, students and learners. So we are here with the module 10 of the material science course from the School of Engineering Technology in the Gandhi National Open University. I am Shashank Srivastava, and we are covering the unit 2 of your course, that is entitled as Engineering Alloys Ferrous and Non-Ferrous. So before this we have discussed up till the time transformation diagram, and now we are moving forward. So here we are discussing a very important aspect, that is heat treatment. It's a very important thing, so we move with this now. So a range of properties may be produced in steels because the structure of various phases of microstructure depend upon the rate of cooling. So depending upon the rate of cooling, the microstructure changes and we get different kinds of steels. So this heat treatment is very important because we can get different things due to this heat treatment process. So what is actually heat treatment? We need to know. So this heat treatment process consists of three main steps. The first is the heating of the metal to predetermined heat treating temperature. Then what we do, we soak the metal at that temperature until the structure becomes uniform throughout the section. And further, the cooling of the metal at some predetermined rate, such as will cause the formation of the desirable structure. Okay, so while discussing about the heat treatment, we should also know that it is normally applied to hypoeutectile carbon steels. Hypoeutectile, like we have discussed earlier, hypo word is used for something which is lesser. So this hypoeutectile means that the carbon percentage is lesser than 0.8%, because 0.8% is the eutectile carbon steel. So the heat treatment processes, basically they are named as annealing, normalizing and hardening. So we will be discussing them here. The temperature to which heating is done in all these three cases is about 50 degrees centigrade above the A3 temperature, like we have discussed earlier. The A3 temperature is the 910 degree centigrade temperature in the iron carbon phase diagram. So here is the figure for that. You can see here we start this process, like there are three processes you are seeing in the figure. The first one is the annealing, the second one is the hardening one, and the third one is the normalizing. So if you see the left hand side of where the temperature axis is there, so you can see 900 degrees centigrade. So all of these three processes are starting near about this temperature only. But the difference is that normalizing is temperature is somewhat higher than the annealing one. So it follows the line A3 while the cooling takes place, and this curve comes down to the eutectile point, that is 0.8% carbon. And further, when full annealing is there, it is following the straight horizontal line around 723 degrees centigrade. So one more line you can see, the ACM line, that was about the gamma austenite portion phase where the cementite and the ledoborite were there. So from there, if the cooling is taking place, it is following the ACM line and it also comes down to the eutectile point. So these different processes give us the different kinds of things. So we can get the stress relief, or we can get the spheroidizing. Different things are there, which we will see. So it is a heat treatment, basically is done to soften the steels. So if we want to soften the steel, that heat treatment process is being taken over. The heating and cooling both are done at controlled rate in a furnace. Hypoeutectoid steels are heated above the upper critical temperature, that is the A3 line, like I told you earlier, 910 degrees centigrade, while the hypereutectoid steels are heated only above the lower critical temperature, that is the A1 line, which corresponds to the 723 centigrade temperature. So the cooling is done such that gamma to alpha transformation goes to completion to each temperature. So this is the way of cooling, that gamma to alpha transformation is taking place at every temperature, meaning from austenite to ferrite transformation is taking place. The resulting structure consists of large grains of ferrite with coarse perlite, in which thick plates of ferrite and carbide are present. So if we see after the cooling, we come to the eutectile point. So the ferrite is there, large grains of ferrite are there with coarse perlite. coarse perlite meaning it's not fine and the grain growth is more. And so thick plates of ferrite and carbide are present. This is softest possible structure and is ideal point for starting mechanical working of steel. When we look at ferrite, it is the softest possible structure. That's why its mechanical working can take place. And it has low yield strength and the tensile strength is also very less for ferrite. So the different things or purposes which are achieved through annealing, now I am listing for you here. The first one is the relief of internal stresses within the metal. So when we do annealing, the internal stresses are removed. Second is that the production of uniform grain structure throughout the metal. So we get a uniform grain structure throughout the metal due to the annealing process. And the third purpose is that softening of the metal takes place. So annealing has these three basic purposes, and it can be further classified as full annealing or process annealing. What is full annealing? Full annealing consists of heating a steel to above the upper critical temperature and slow cooling, which is usually done in the furnace. So this initial heating is done up till the upper critical temperature, which is 900 degrees centigrade, and the cooling is done in the furnace. However, cooling can also be done in ashes of sand or in specially built cooling pits, lines with refractory and covered with refractive lid. If heated to too high a temperature or soaked for too long a time, the austenitic phase undergoes grain growth, resulting into coarse perlite grains. So if we are heating that steel to a very high temperature and then soaking it for a long time, so it will follow the TTT diagram and we will have coarse perlite grains instead of the ferrite. Such a structure is termed overheated and exhibits low mechanical strength. So the difference between the coarse and the fine is given here in this figure. You can see the coarse, the spaces between the particles is more, whereas in the fine one they are together. It's very compact. So that is the basic difference between the coarse and the fine microstructure. Now after discussing the full annealing, I am now discussing with you process annealing. Process annealing, it is what actually? When the heating is done to a predetermined temperature, which is generally below the A1 temperature. So you can see the difference here. In the full annealing, the heating was done up till the upper critical temperature, whereas in this case it is done below the lower critical temperature, that is A1. The metal is then air cooled or quenched in a suitable pickling bath. So like salt bath was there earlier, so here also it is one bath. Mild steels or hypoeutectoid steel containing less than 0.3% carbon after having undergone the mechanical treatment are softened by this process by heating to a temperature between 550 degrees centigrade and 650 degrees centigrade. So you can see here we are not going up till 723 degrees centigrade. We are only going up till 550 or 650 degrees centigrade. So it is below the A1 critical line. The distorted grains of ferrites in steel are fully recrystallized by the process, this process of annealing, which is called the process annealing. The perlite grains are not affected by process annealing, so that the structure consists of stress-free ferrite matrix with distorted perlite. So by process annealing, what we are getting? We are getting a mixture of stress-free ferrite and distorted perlite. So we were talking about a stress-free things. So here this process annealing is giving us the stress-free ferrite and perlite. So after discussing the full annealing and the process annealing, now we come to the normalizing. What is normalizing? Normalizing is used as a finishing treatment for carbon steels, giving higher strength than annealing. So it's you can say a little higher grade process than annealing. It is giving us a better finished product or carbon steel, and its strength is also more. And there is no serious loss of ductility also in this case. In this process, the heating and soaking is same as in full annealing, but part is allowed to cool in air, so that cooling is much faster. So the difference between annealing and normalizing you can see here. that in annealing, full annealing, we were heating up to the upper critical temperature of 900 degrees centigrade. But in case of normalizing, what is happening? We are heating like that of the case of the full annealing, but the cooling is different. Here the cooling is taking place in air, whereas earlier the cooling was taking place in furnace. So the finer grains are produced in this process because there is lesser time available for them to grow. So earlier we were giving more time because it was being cooled in furnace in case of full annealing. So growth was more. Here the growth is less. So that's why finer grains are there. So the finer grain structure increases the yield and ultimate strength, hardness and impact strength. The ductility is, however, slightly reduced. So we see here that normalizing process is giving us steel which is of higher strength and hardness and impact strength as compared to the annealing process. The effect of a small grain size is more noticeable in impact strength than in tensile strength at low carbon content, say 0.2%. Suppose the carbon content is about 0.2%, then the impact strength is much more affected than the tensile strength due to the small grain size. The tensile strength improves only by 5% in case of carbon content about 0.2%, whereas the impact strength improves by 20% by normalizing as compared to annealing. But at higher carbon content, what happens? We will see now that at 0.4% carbon, it is not only the impact strength but also the tensile strength that improves markedly by about 15%. So when the carbon content increases, both tensile and impact strength are increasing somewhat in the same manner. But in case of low carbon content, impact strength increases much more as compared to the tensile strength. Normalizing often applied to castings and forgings, and why it is done? Because it relieves the stress. It also increases the strength of medium carbon steel to some extent. So medium carbon steel strength is increased by the normalizing process. So these are the benefits of this process. When applied to low carbon steel, it improves machinability. So when it is applied, this process normalizing is applied to low carbon steel, it improves the machinability. So we have seen certain advantages with medium carbon, with low carbon, all these things. Normalizing process is giving us quite a lot of benefits. Alloy steels in which the austenite is very stable can be normalized to produce hard martensitic structure. So in case if the austenite in a certain steel is very stable, and a normalizing process can be applied and we will get good hard martensitic structure. Cooling in air produces high rate of cooling which can decompose the austenitic structures in such steels, and martensite can be produced. This increases the hardness to a great extent. So whenever we want to increase the hardness, so we can apply this normalizing process wherever the austenitic structure is stable. So here we see one table. So the conditions are given here, the annealed and the normalized type of steels, and we can see the structural steel low, medium and high carbon content, so and the total steel. So you can see the hardness of the annealed and the normalized carbon steels. See, annealed is 125, then normalized is 140. So this is the thing, that hardness is also varying. In case of normalized, we can see that the hardness and all things are somewhat better than the annealed ones. So this table is telling about that. Further, one more table where you can see the variation of annealing and normalizing temperature and the resulting hardness for different carbon contents. So you see here like 0.18 to 0.22% carbon, you can see the annealing temperature is 860 to 900 and normalizing temperature is 900 to 925. So they are in the close range, but normalizing is always somewhat higher than the annealing. Similarly, hardness, if you see the Brinell hardness number is given in the case of 0.18 to 0.22% carbon range. 110 to 149 is the hardness range for annealing process, and for normalizing it is 120 to 160. So here also the normalizing is giving somewhat better results. So this will be similar in all other carbon percentage range of various steels. So now we can discuss the hardening process. if a steel part is heated 30 to 50 degrees centigrade above the A3 temperature, that is the temperature of 910 degrees centigrade in the iron carbon diagram, complete austenizing is permitted. And then we can see it is the range where gamma is completely present, gamma in a certain carbon percentage range. Gamma is nothing but austenite, so that is permitted. And then by soaking at that temperature and cooling suddenly, quenching, if you are cooling suddenly, it is also known as quenching, so the breakdown of austenite is suppressed. The new phase that forms is martensite, in which all the dissolved carbon is held in form of body-centered tetragonal structure. So it is still body-centered structure like we have in case of ferrite, but now it is not body-centered cubic, but it is body-centered tetragonal because of the distortion that takes place in the microstructure. So you can see here the unit cell of the distorted body-centered tetragonal lattice of martensite. So we can see that one length is given by the alphabet C and the other length is given by the alphabet A. So A and C are no longer equal, and you can see the Fe atom, which is the iron atom, which is placed at the end of the edges, and the carbon atom is in between the two iron atoms on one of the edges. So this is causing the distortion. So the length changes and it is no longer a cubic structure, but it is a tetragonal lattice. Martensite is only metastable phase and maybe tempering also. So tempering is also a process where we can improve the steel, and it is done at temperature below the lower critical temperature only. Basically it is extremely hard and brittle and has a characteristic acicular appearance. The martensite, again, as we have discussed earlier, it has acicular appearance and it is hard and brittle whenever we examine it under a microscope. In the steel sub-2 eutectoid composition, the martensite formed by this drastic quenching operation contains all the carbon that was contained in austenite. So if the cooling rate is very high, the carbon is still there, which was there in the austenite, but it is still there in the martensite phase also. In higher eutectide steels, however, some carbon is converted into carbide particles also. So that's the difference. In case of higher carbon percentage, this carbon can be converted into carbide. Carbide is what? Fe3C, like we had cementite. So similarly carbide is there, and it is not free carbon. But in case of hypoeutectoid or below the range of eutectoid, the carbon is there in free form in the martensite. So now we discuss about the martensite hardness variation, how the hardness of the martensite itself varies. So hardness of martensite is dependent upon the percentage of carbon present in the structure. So like elsewhere we have seen earlier also we have discussed, like carbon percentage determines our hardness. So here also is the case. So this figure is illustrating that thing. If you see the red line is marking the 0.8% carbon, arrow is there which is showing 0.8% carbon, and leftward and rightward the variations are there. So we can see from this figure how the hardness varies with carbon content. So one curve is showing us the hardness as quenching takes place, and the other is showing us hardness when annealing takes place. So in case of quenching one, you can see carbon percentage is on the x-axis and the Brinell hardness is on the y-axis. So in case of the quenching one, the rate of increase of the hardness is high. So it is increasing quite largely, and it goes up to a certain percentage of carbon 0.8% you can see. Then it stabilizes somewhat, and further it increases, and after that it comes down. And then you see the curve of the hardness as annealed, which is marked as hardness as annealed. You can see it's quite a parallel curve to the x-axis. Only slight increase is there after the 0.8% carbon. So it can be seen that hardness of plain carbon steels increases rapidly until the eutectoid composition is reached. So if there are plain carbon steels, the hardness increases until the eutectoid point, 0.8% carbon point. After this composition, the hardness increases very normally. It's not a drastic. So here also again the same graph is there, and we can see from this two arrows are there, red marked, red arrows. So you can see from 0.8 to 1.8% of carbon. So hardness as quenched graph you can see, and the hardness as annealed graph you can see. So in the annealed case, this is going somewhat higher and higher with a slope which is quite low. And in the case of hardness is quenched also, the graph goes towards the upper side, but then it has a maximum and then further it comes down. The fact is that the hardness martensite is formed at the eutectoid composition, that is 0.8% of carbon. This is the hardest martensite. The slight increase in hardness of hypereutectoid steel is due to formation of carbide particles which are hard and brittle. So the reason behind the graph going up beyond 0.8% also slightly is the formation of carbide particles which also increase the hardness. And one more thing in the graph is there, that is the percentage hardness increase after quenching. So the percentage hardness increase, here we are talking about the increase, that means the rate of hardness. The time factor is there. So we can see that in the case of rate of hardness, it is quite high in the beginning up to 0.2% of carbon. Then there is a maxima and further it comes down. That is after about 0.25% carbon, you can say that this rate of increase of hardness is not that high as compared to the earlier portion of 0.2% of carbon. Now we will discuss the cooling rate and the effect of the quenching media. So how does the cooling rate affects the formation of the martensite? Rate of cooling plays an important role in determining the final structure after quenching, especially in case of the eutectoid steel. Figure is there which illustrates 4 different structures that are obtained by different cooling rates when austenized steel is cooled in 4 different media. So here the figure we can see from this one, it is about the microstructure resulting from different cooling rates applied to austenized samples of eutectoid steel. So further we see that there is the martensite, and there is a very fine perlite in the figure, fine perlite and then coarse perlite. So it all depends on the cooling rate. See the arrow curves you can see. If there is furnace cooling, then it results in coarse perlite, meaning the grain growth is more and it gets time to grow. Then there is the air cooled, meaning fine perlite, meaning the structure growth rate is lower. They are not completely grown, they are in small parts, small shapes, so that's why they are fine. Further there is oil quenching. When we are doing oil quenching, then we are getting very fine perlite. So it's better than the fine perlite in terms of the compactness. And if we are doing the water quenching, then we are getting the martensite. Most portion is martensite, a little bit of portion is cementite. And in case of the eutectoid, we are getting the perlite, 0.83%. So it's a mixture of the ferrite and the cementite. This is the same iron carbon diagram which we have discussed earlier also. Only the drastic water quench, it is said, produces a fully martensitic structure. So if somebody needs a fully martensitic structure, then he has to do drastic water quench. Otherwise there will be a mixture. Very fine perlite structure that is obtained from oil quenching is also known as the primary torosite. So here we see a table which is about the mechanical properties of eutectoid steels after cooling in different quenching media. So you see here the cooling media, there is water, oil, air and furnace. So from the water we are getting the structure of martensite, from oil we are getting torosite, from air cooling we are getting fine perlite, from the furnace cooling we are getting the coarse perlite, which I have discussed in the diagram also. So here we can see one more thing, the ultimate tensile strength and the yield strength as well as hardness and elongation. So you see in case of water quenching, the ultimate tensile strength is 1700, the yield strength is not there, the hardness is 65 and the elongation is very low. So water quenching, what it is giving, now you can understand by yourself why YS is not there, because I have told you earlier also. Because we are getting a material, if you see the elongation there in the table, it is low. That means we are getting a brittle material. So a brittle material, if you recall from your first module, how the shape of the stress strain diagram is, it doesn't have any yielding. So that's why yield strength is not given in case of the water quenching martensite. And further, if you see with the oil, the ultimate tensile strength is lower than with water quenching. It is only 1100 Newton per millimeter square. Why it is so? Again, you have read in the course the compression test in the second module that compressive strength, ultimate tensile strength is higher for many materials than the tensile ultimate strength. So now I discuss the effect of water media. What happens when this water is used for the quenching process? So water as such is the cheapest quench media for plain carbon steels, but care must be exercised while using water. Certain precautions have to be taken. It has to be properly agitated during this treatment, else air bubbles are formed and they may be trapped on the surface and insulate the spots, from which heat flow will be delayed. So such spots will then result in softness. So the hardness will be affected ultimately. Then salt water or brine is more severe quenching media. If we want even more severe quenching, meaning cooling rate even higher, then we use salt water or brine. Brine, like chemical formula, is NaCl, so it is used. So what it does, it removes heat faster than plain water. However, in this case, the steel must be thoroughly cleaned after quenching. So again, a precaution is here that it should be thoroughly cleaned, because what will happen otherwise, the surface will begin to rust, because it has a corrosive property. The salt water has a corrosive property. So after this water media, there are other medias, like for very low carbon steels, hydroxide solutions are often used. Instead of brine, like instead of NaCl, we can use NaOH, that is sodium hydroxide. If slower cooling rates are desired, the steel may be quenched in oil with high flash points. So a slightly slower cooling rate is desirous, then we can use oil. So various grades of quenching oil are also available. High carbon steels are invariably quenched in oil, since water quenching will develop cracks in such steels. So with high carbon steels, we never use water, instead we use oil, because it helps us to get rid of the cracks which will come due to water quenching. So further we come to the hardenability of a steel. We will now discuss this aspect. So loss of heat of a metal piece by quenching is dependent on several factors. So whenever we are doing quenching, so how the heat is getting lost from the metal, it depends on various factors. But on face, it can be easily understood that the loss will not be uniform over total volume. So this loss of heat, actually, if you see there is a body or a specimen, so that loss of heat, we cannot say that it will be uniform over the whole body. So that part of the metal, generally it is seen, which is in direct contact with the quenching media, will lose heat faster than the inner side. So it's obvious also, you can see, like if there's a specimen and you put it in water, so the part which is coming in contact earlier with water will be getting cooled earlier also. So this will bring thickness or the diameter of the part into focus, because if it is a very thick object, then the heat loss from the inert part will take a lot of time. So the thickness or diameter of the part is in focus, and it plays an important role in hardening. This figure, you can see temperature and the cooling curves are there, and hardened region you can see. So it shows the cooling curves for the surface and for the material just below the surface and the core. The cooling rate inside the material is governed by thermal conductivity of the steel. So we all know the thermal conductivity of different materials are there, and upon that depends the heat loss from that particular object or body. And this is also the function of the thermal gradient existing within the piece to be hardened. So there is always a possibility that at the inner core the rate of cooling is less than the critical rate, resulting into unhardened material there. So all possibilities there that the outer part of the object or the specimen is hardened, whereas the inner part remains somewhat soft because the heat loss hasn't occurred in a proper manner. The depth of the hardened layer is the measure of the hardenability. Suppose a material is thick up to a certain portion, then the depth of that hardened layer will give us the measurement of the hardenability. So a good hardenability will mean even thicker sections are uniformly hardened. Suppose there is a very thick specimen, and if it is hardened in a proper manner, then even its inner portion will be quite hardened. But if it is not a good or a hardenability, or you can say poor hardenability, then it will produce a soft core inside the piece of the steel. So outer portion will be hard and the inner portion will remain as soft. So in this module we have seen the process of heat treatment, and basically there are three kinds of heat treatment processes: annealing, normalizing and hardening. So we discussed the advantages of these and what are the purposes of these annealing, normalizing and hardening. And now further we will see in the upcoming lectures the things which are going to come up. Thank you very much.